What we're looking at here is a model for charge movement in semiconductors, and an intrinsic semiconductor is one that has basically all one type of atom in it, and we predominantly look at it as an intrinsic semiconductor. And you can see in the case of silicon, it belongs to this row here, this column, and the one next to it we have boron, and the one next to that we have common ones that are used in semiconductors. The silicon one, all of this row has 4 valence electrons, or 4 electrons in their outer shell. This one here, 3 electrons in its outer shell, all of them, and this one, we've got 5 electrons in their outer shell. If we take the case of silicon in particular, the first one is silicon, the one we mostly cross, and we see it's got 14, which means it has 14 protons. And to balance that, because each atom is neutral, unless it's an ion, in this case they're atoms, it has 14 electrons. We're only really looking at the outside electrons, as they're the ones that are taking part in what this atom is doing. So here we have a silicon atom, and you can see the outer 4 electrons. These silicon atoms have joined together. They want to have 8 electrons in their outside shells. So when they join together with other silicon atoms, as you can see here, each one has 1, 2, 3, 4, 5, 6, 7, 8. Each one only has 4 of its own. The others come from the next atom. Okay, so when they form this lattice structure, each silicon atom has 8 electrons around it, and that's the most stable state. So what we have here is an intrinsic semiconductor. Because each silicon atom is quite stable in this structure, when we apply electric field to it, so a minus end and a plus end, or vice versa, it's difficult to get the electrons moving. So we apply our electric field, electrons might start moving if a high enough voltage is applied, but in general each silicon atom is stable and they'd like to stay this way. We need to then add new energy to this structure, and that could come in the form of UV rays, UV photons of energy, enough to get electrons to start moving out of their shells and leaving a hole behind. In the next video we're going to see that happening. So here we have a short video, and you can see each one has 8 around it. It's the central silicon atom here. You can see that it has these 8 pairs of electrons, 4 pairs of electrons. And when we press play on this, we have a source of energy, which is going to give some extra motivation for those electrons to move. We can say so there's our energy. Here we have our first electron moving onto the next atom. These are delocalized, leaving a hole behind. Another electron can move into it. Another electron can move into that, leaving a hole behind, and so on. So as these electrons move around, the holes move one way and the electrons move the other, and our holes move this way. These holes are not anything in particular, they're an area that is more positive than the electron area, which is more negative. So positive holes are our positive charge carriers moving towards, in this case, a negative field. Our electrons might be moving the other direction towards the positive part of that field. So we have a potential difference or a voltage applied across this. The flame provides the extra energy that's needed to get those electrons to start moving from their stable or more stable silicon atoms. So we can look at this. So we can model the movement of charges through a semiconductor using a checkerboard, where the checkers represent electrons. The nuclei of the silicon atoms are represented by coins, and as we move these around we can leave positive holes and see how the silicon structure works. So in this case an electron would move, and that could be because we've added heat or we've created an electric field around a checkerboard. So here we've got a positive side and a negative side. We've created a voltage across this semiconductor. As we receive extra energy either from heat or from solar energy, so photons from the sun, these electrons start to move, they leave a hole behind, and then another electron can move into it, leaving a hole here, then another electron can move into that, leaving a hole here. So our positive charge carriers are represented by holes or squares where there's no electron or no checkerboard piece. The part where the checkerboard piece is gone, so that becomes a positive hole. The electron itself is a negative electron that's represented by the checkerboard pieces. Is at a battery or a power source to this semiconductor. So at the top here, we've got a battery, positive and negative end. I'm adding a wire to one end of the battery and a wire to the other end of the battery, so that electrons can leave this battery and head around the wire. So there's just one there to show an electron. We'll put another wire here, another wire here. A wire here and here. You can see there we have a simple circuit that's not touching anything. And the fact that we've got those two wires on there, we're setting up a field on either side of this intrinsic semiconductor. Now if we increase the voltage enough, or the potential difference from one side of the battery to the other, so we increase the voltage of the battery high enough, it can cause some of these electrons to start moving. Now electrons will move towards the positive side and be taken from, so as one leaves there, another one might come from the battery to fill in that gap. And they'll move across and then round the wire in order to complete this circuit. You're going to need a higher voltage, but because this is a semiconductor, it's not a good conductor like a metal. It only conducts under certain conditions. You can see the electrons moving from the battery around and into this side of the semiconductor. You need a high enough voltage to make them want to cross this gap in order to complete the circuit. Another way to cause this energy or electrons to move across the semiconductor is to replace some of these silicon atoms so that you have extra electrons in the solid. Now we know that silicon, it has 4 electrons around it, in its outer shell, 4 valence electrons. And we can see that if we look on a program like this. You can see the periodic table here. Silicon is in this group, silicon here, and phosphorus here. You can see there's 5 electrons in the outer shell. Boron, there's only 3 electrons in the outer shell. So silicon is out. So we want to make this electric current flow more efficiently. We can change the nature of this semiconductor. If you look on the periodic table, silicon here has 4 electrons in its outer shell. Boron has 3 electrons in its outer shell, and phosphorus has 5 electrons in its outer shell. We can make use of those facts. We can use any of these. So these are the group 3 elements, group 4 elements, group 5 elements in the old group naming structure. Carbon also has 4. Germanium also has 4. So silicon's the one we're using. And what we can do is replace some of these silicon atoms. If we use phosphorus, we'll have extra electrons. So we're just going to do that now. As we said, phosphorus, and we put them on. Here we've got phosphorus. Another one, another one, another one, another one, another one. So there's 6 in there. Phosphorus has 5 electrons in its outer shell. So each phosphorus atom has an extra electron. And if we put those on, we'll see that we've done something to this solid. So here we can see, as we keep adding, and there should be one more phosphorus here. Oh, they've all got their extra electron. You can see, even though the silicon, they're not ions, they're atoms. They're neutral in charge. Phosphorus are neutral, but each phosphorus has 5 electrons around it. The silicon has 4 electrons around it. So by adding phosphorus to this semiconductor, or doping it, we call it doping, much like adding a foreign substance, we've doped this silicon semiconductor with phosphorus. We now have an excess of negative charge carriers. They belong to the phosphorus, but they're extra to what the silicon had before. So now when we put our current on, these electrons more easily across and leave holes that other electrons can then enter and fill. So we've got electrons moving this way and little spaces moving the other way. We'll see how they work again in a sec. We can also dope with boron, so I'm just going to set it up to show you what the boron would look like. So you can see here our semiconductor has boron instead of silicon atoms. And those, it has the silicon atoms, but it has boron added to it. It's been doped with boron, and boron is from group 3. So it only has 3 electrons around each boron atom, and that's adding to the silicon atoms, which need 4. So around each boron we'll have a space or a hole, and we do that. We can just remove these and see how it looks. Another boron there. So we've got 2 gaps. Now we call this because and everything's all charge neutral. The borons have 3, the silicons have 4, and we can see some gaps have been left because the borons have 1 extra electron missing. Remember, these are pairs, but we've had to remove it to represent a hole. This hole is an area that's more positive than the areas around it. There's no electron there, but there's a hole here where an electron might move into. And we see what we call this is a positively charged semiconductor. So it has extra positive holes, we call them. If we apply our field to this, and we can see electrons can move into those positive holes, and as electrons move into those holes, the electrons move one way and the holes move the other, and then for other electrons can then move into those. So you can see the hole is now moving this way and to here, but the electrons have moved that way towards the positively charged end of the field. So that's a p-type electron, p-type semiconductor. Uncluttered the board now. You can see we've still got our field applied, and if we have the boron doped semiconductor, we'll have the extra holes. And what they mean is when you turn on the current and electrons come in to fill a hole, those electrons will move across the field this way. So as it moves across, the electron went one way, the hole went the other. Again, you can see that here, electron is now moved to here, and the hole is left behind. This is for boron. Again the hole, again the hole, again the hole. So the hole's moving one way and the electron's moving the other. This is our model of how charge carriers move, electrons and positive holes move in a semiconductor.